Okay, here we go. So today, everyone, we're going to talk about stuff. Okay? The scientific word for stuff, that's the way I think about it, is matter. Matter, by definition, is anything that takes up space and has mass. Matter is anything that takes up space and has mass. Anyone by raise a hand know how to define the difference between mass and weight? Just so we make sure we understand those. Yeah, Max?
So mass is like how much stuff is actually in a molecule, and then weight is the gravitational pull on that stuff.
Very good. Have a smiley face for that, Max. So lots of times we think of them the same, but they're not. And mass is always what we want to use in chemistry, because weight is just based on gravity, right? This is the way I think about it. That makes the most sense. A scale that measures weight works through a spring compression system, meaning you step on the scale, the springs compress, and you get your weight. Well, the reason why the springs compress is because gravity is pushing on you, right? That's why if you go on the moon, your weight is less because there's less gravity. The way we determine mass is through a scale-based system, meaning, okay, this is 1 pound, how much does this weigh in comparison? Everything that is a unit of mass is just arbitrarily determined. Someone just decided at some point in history, like, hey, this much stuff we're going to call a pound. That's all that means, right? That's literally just where measurements come from. If someone decided that's how much it will be, right? Or in case of chemistry, we'll use grams. They said, okay, this is how much a gram is. So when we use mass, like Max said, it doesn't ever change, because the amount of stuff in you doesn't change just because you go to the moon, right? So by raising hand, can anyone think of something that would not be classified as matter then? If that's what matter is, what's not?
Light.
Good. Yep, light would definitely not be matter. Good. Have a smiley face. Other examples of something not matter?
Well, from that, probably sound.
Good. Yes, sound, not matter, right?
Just anything waves.
Good connection, right? Things with waves. What else travels in a wave besides light, sound?
Radiation.
Good. Radiation. I'm going to even expand that to energy, right? So anything that classifies in that energy bubble is not matter. Outside of energy, everything else is, right? Which that's why I say it's the scientific word for stuff. It's because most things are matter. So let's break down matter into some further classifications. So one of the first ways you can classify matter is by how it looks, okay? And when you look at it, you can classify it 2 ways. You can classify it as a heterogeneous mixture or substance, or a homogeneous mixture. So heterogeneous and homogeneous. This level of classification is purely by what your eyes can see. Okay, so this is purely, here's my little eyes. Purely by what your eyes can see. A heterogeneous substance is a substance that looks different. The scientific ways, they say it's not uniform throughout. An example of a heterogeneous substance would be granite, right? If you look at a piece of granite, everyone knows what granite is, right? Nod your head if you don't, so you can pull up a picture. Okay, but a piece of granite, you can see lots of different specks of different things. A homogeneous substance looks the same throughout. Once again, keep in mind, it looks the same throughout. So an example of a homogeneous substance would be salt water. Okay, if I have salt water, can I see the salt versus the water? I mean, I guess depending on where you're at, you could, like Great Salt Lake, you can. But generally speaking, right, if I put a scoop of salt stirred around, you can't see the different pieces. So another way you can think about it is hetero is always 2 or more things. Homogeneous could just be one, such as pure gold. Gold is a homogeneous substance because it literally is just one thing. But it could also be a combination of things that look the same. Okay, turn to your table buddy, which is the person you're sharing the table with, and see if you can come up with another example of a heterogeneous and a homogeneous one together. Ready, set, go. Something in the world that would be Okay, raise a hand. Let's hear a few more examples to make sure we're all on the right page. Someone give me an example of another heterogeneous substance. Anyone? Yeah.
Dirt, since it has different types of.
Yeah, I'd say generally dirt is heterogeneous because you can see lots of different things, right? I mean, I guess if you got a really, really pure type of dirt, you wouldn't. But generally speaking, yes, good. Have a smiley face. Another example of a heterogeneous one? Oh, you guys have homogeneous ones? Give me a homogeneous one.
Oh, no, I said heterogeneous.
Oh, another one? Yeah.
I said sedimentary rock.
Yeah. Yeah. Yeah, I mean, you can see the different layers in it, right? Good. Have a smiley face. Kimberly.
We said like a chocolate chip could be because you could see the chips and then.
Yes, a tasty example. Good. Have a smiley face. Good. Okay, flip it. Someone give me an example of homogeneous substance. Yeah.
Like silver.
Silver. Perfect, right? Pure literally is just one thing. Good. Have a smiley face. Carly.
I said water, and I also really liked Kimberly. She said like a cake, and actually like a cake without frosting.
Oh, yeah.
Looks like
Because, I mean, if it's not like funfetti or something, right? It's going to be just one thing. Good. Have a smiley face for that.
Jello.
Jello. Ooh, that's a good one, right? It's a combination of things, but when you look at it, you can generally not see it. Good. Have a smiley face. Okay. Any other questions before we classify further? We understand kind of the difference of those two? Okay. Now, heterogeneous substances are always going to be mixtures. A mixture is a combination of two or more things mixed together, hence the name of mixture. Okay? A homogeneous substance can be a mixture, but it also can be just a pure substance. Okay, so now let's talk about the difference between these two things. So, last time, the balloon. Remember that on the ceiling? Right? Did I tell you what was in it? Oh, so that was hydrogen gas is what I made in that reaction. Okay, so I'm going to draw, it's simple and wrong, but it's a start of a picture just to get us somewhere. Okay, so hydrogen, right? Here's my little hydrogen atom. Okay, so in that balloon was hydrogen. There's also some oxygen, so hydrogen, oxygen. Okay? That balloon would be classified as a mixture of these two things. It'd be also classified as homogeneous because you can't see the difference between these two. They're both gases, they're both clear. They're both in this room right now and we can't see them. It looks like one thing. But if these atoms bond together and make this substance, known as H2O, all of a sudden it becomes a pure substance. So this is a pure substance by themselves. Even if we were to draw another hydrogen, there's a mixture. So before I define it officially or go into it more, turn to your table buddy and tell them if you feel like you can, explain to them what is the difference between a pure substance and a mixture. Ready, set, go.
So pure
It just has like
So when they're separate, then they're just
Thank you. And I know at times I'm going to ask you to discuss things that you're like, I don't really know how to say it, right? But I encourage you to just try, right? This is a time to sound silly, throw things together to get that brain working, right? It's okay to be wrong in here, right? But I'd rather have you try and be wrong than not try at all. It does so much better for the brain. So, okay, I heard a few good things as we discussed that. With this idea, this substance right here, when atoms are linked together, and we'll learn a ton about bonding as we go on, okay, this right here is classified as a compound. So H2O is an example of a compound. These by themselves are classified as elements. So pure hydrogen by itself is a pure substance. Oxygen by itself is a pure substance. When two pure substances are together but not linked, it is now a mixture. Okay? So we're going to do a test here just to kind of see how we're doing. I'm going to write 3 examples, and I want you to just take your best guess of understanding. Label this thing as a compound, an element, or mixture. So put an M, C, or E next to these examples. Just on your own as best you can, okay? So on your paper, classify for me milk. So just take your best guess. What would milk be classified as of these 3? Okay, next one, classify gold. And the third one, classify sugar. Okay. Everyone good? Turn to your table, buddy. Compare your answers to theirs. If they don't match, discuss maybe why, and then we'll group back up. Go. Okay, here's some sign language for you. Ready? So this is an M. You don't know. M. C. E. So you're just going to show me what you put. Got it? Okay, show me what you put for milk, everybody. Okay. All right, can someone feel like they can defend why milk is a mixture?
no.
Max, defend it for us. Why?
So I was just thinking, and I know that there's water in milk, which is a compound, and I also know that there's sugars in milk and a lot of other things. So since it's not an element and not a compound, it's a mixture of all.
Good. Anything with an ingredient list is a mixture, right? All those ingredients aren't linked together, they're just all in there together, right? Great. Have a smiley face for that. On that same line, something else you can kind of use for mixtures, and you gotta be careful with this word, but mixtures can be easily separated. Can milk be separated into different components? Does natural milk separate on its own? Yeah. Right, I know we buy it at the store, so that's already like mixed together. The milk will naturally separate on its own. If you freeze it, actually, you can see it separate a little bit, right? Now, once again, I say easy because sometimes it's not as easy as others, but if you can literally pull the parts out physically, then it's just a mixture. It takes a lot more work to separate a compound. For example, with water, if I wanted to separate these from each other, I have to send electricity through the water, and then I can get it to separate. But it's not an easy process. It's not as easy as a physical separation. So, good. Okay, show me your vote for gold. Very good. Element, pretty much if it's over there, it's an element, right? If it's not up there, it's not an element. Don't go looking for the symbol for milk, right? You won't find it. Okay? Okay, and last, sugar. Show me your vote. Sugar is classified as a compound. Good. Someone want to defend for us why is sugar a compound? Yeah, Evan.
Because sugar is a mixture of elements.
Good. So number one, it's not an element, right? There's no sugar up there. There's a variety of formulas. Sugar is a very broad term. There's lots of types of sugar: fructose, glucose, sucrose. The one we're most familiar with is C6H12O6, right? So it's a combination of elements, like Evan said, and they're linked together, okay? So often, have a smiley face, Evan. Often the way I view the world of chemistry, it's simple, but once again, simple can often be the best to get you started, is I think of the elements like Lego blocks, okay? One of the craziest and so cool things about chemistry is the difference between separate Legos and stacked Legos, okay? Here's an example. Oh, by the way, you can have a smiley face for every one of those you got right, so up to 3. Okay, so for example, if I were to get the Lego block of sodium, okay, so pure sodium, and the Lego block of chlorine, this will explode your tongue if you ate it, and this will suffocate you. But if I stack those two Legos together, what do I get? Salt. Right? Which we need. So this is death, this is life. What's the difference? Just that little tiny bond, right? If we think of our chemistry triangle, it's crazy. The only difference on the symbolic side is a little plus sign. That's it. But if you go to the macroscopic, what we see side, it'd be drastically different, right? This is a little white crystal. This is a yellow gas. This is a silvery metal. But when you take these two things and bring them together, they change so much. Okay, some of you are not looking as like amazed as you should. This is crazy, okay? Like, look, this is explosive. This is explosive. We drink this? Right? Literally made up of the same pieces. But when things bond chemically, it changes them so much, right? Let's talk about my periodic table just for those that aren't familiar with it, okay? So the way mine is set up with the color coding system is all of these elements that are white are called, they're man-made elements. They've been made synthetically in a lab. You can't find them just on the earth. We'll talk about how they do that later, but just know that. All the rest are found naturally. The black ones are solid at room temperature. The red ones are gases at room temperature, and then the blue, there's only 2 blue ones, but those ones are liquid at room temperature. Okay? So what is so crazy about this study of chemistry is that the entire world, the entire universe, is literally made up of 92 Legos, and that's it. So everything in the world we see, from this pencil, this tiny, are made up of the same pieces, to some extent, right? And I'm not like comparing her to a pencil, it's a true for all of us, right? That everything in the world goes down to those, and it's really less than 92 because a lot of them aren't even used in things. When you study organic chemistry, you find that most of living things are broken down to a very small grouping of 20 elements, and that's it. Which is so crazy by that linking property. So, okay, any further questions with classifying between these three? Any other clarifications we need? Now, this right here, when something is a homogeneous mixture, it does have a special name. It's known as a solution. So solutions are substances that look like one thing. They're homogeneous, but they're made up of a mixture of things. So salt water would be an example of a solution. Once again, it's a mixture. It's salt and water. But once you mix it together, you can't really see the different components. But being that it's a mixture, can you separate salt water fairly effortlessly? Yeah, you just boil the water, right? I'll separate it off. So, okay, now what we're going to do, let me make sure when I teach a lesson twice, I don't want to miss something. Okay, we're now going to zone in on this box. Okay? Elements are identified as atoms, or a specific type of atom. So an element is just a specific type of atom. Atoms are defined as the building blocks of matter. Everything else is made up of atoms, or aka elements. Atoms, as we'll build a second flow chart here in a second, can be broken down further. But they're considered the building block because they maintain their identity at that level. So for example, let's say I had a brick of gold. That'd be really cool, right? Actually, it's really heavy. Okay, but I have a brick of gold here. If I took that gold brick and I cut it in half, kept cutting, cut, as small as I could go, the smallest piece you can get down to, and it still behave as gold, meaning it looks like gold, it smells like gold, it acts like gold, is an atom. If you cut that atom in half, it doesn't behave like gold anymore. So that's why atoms are considered the building blocks of matter. So I'm going to erase mine. You can keep building, but we're going to make an entire flow chart now about atoms. I'm just going to erase mine because I ran out of room. But you can decide how you want to. Look at that red marker's kind of sticky. By raising hand, random question, but it does relate. Any of you fans of the TV show Flash? Anyone seen that? You? Okay. Some of you will know what I'm talking. You don't have to have watched it, but it's kind of just a fun, cool connection. Okay, so atoms. Let's start here. Atoms are the building blocks of matter. Okay, atoms are our little Legos that make up everything else. If you take an atom, it can be broken down into smaller things. Now, I just want you to know so you don't think I'm deceiving you or hiding anything. There's so much more to the atom than what we're going to talk about in this class. The primarily thing you learn in high school, or in any science class, which you've probably learned before, is what are the three main components of an atom? Protons, neutrons, and electrons, right? So I'm going to say it like this. So atom has two parts. It has the inner portion known as the nucleus, and it has the outer portion, which I'm going to call the cloud. So this is the middle of the atom, this is the outside of the atom. Okay? Now inside that nucleus, so here's my little model, okay? This right here would be the nucleus, this middle portion right here. The nucleus is composed of two main components. They are known as protons and neutrons. Now, protons are positively charged particles. There's a little plus sign, they're positively charged. Okay? In the scale of atoms, we use a very particular measurement for weight because measuring an atom by a gram is insignificant because it's so small. So the unit that we use for atom size is called an AMU. It stands for atomic mass unit. And a proton is approximately 1 AMU. So this is just its mass. It has some decimal places, that's why I say approximate, but we don't really care about that right now. Okay? Protons are the identity of the atom. They are its DNA. If you change the number of protons, you change the atom. Okay? Now, let's draw a little box here in relation to the periodic table. Okay, so I'm going to do carbons. There's a 6 up here, C in the middle. It's about 12.01. So the periodic table is organized in lots and lots and lots of different ways. There are so many patterns available to us, and that's one of the big things we'll learn in Unit 1. For now, let's just look at these individual squares. The number up top right here is known as its atomic number. The atomic number is the number of protons of that atom. Once again, meaning you change the atomic number, you change the atom, right? If it has 6, it has to be carbon. If it's carbon, it has to be 6. That can't ever change. If it does, it's a new element. That's pretty much how they make, in simple terms, that's how they make the man-made ones. The particle accelerator on the show The Flash, those things are real. They exist. Now, I don't know in terms of exist in making The Flash, but there's one in Louisiana. I think there's only one in the United States because they're so big. But pretty much to make a new element, all they have to do is add another proton to it. Now, it's not as simple as it sounds, but that's really all it takes is just you add another proton and you'll make a new element. Kind of the same thing happens, another pop culture reference, but in Iron Man 2, he makes an element, a brand new one. I don't remember what it's called. There we go, thank you. Right, and he does the same thing. He builds a particle accelerator in his house, right? So, anyways, side note. We should build them. That should be our new project this year. It's so crazy. You should look at pictures, though, of, like, the actual one. The biggest one is in, oh, shoot. Switzerland or Sweden? Is it Switzerland? The Large Hadron Collider? I think you're right, Switzerland. But they're huge. Like, they take up so much space. Like, it's tunnels and tunnels underground to send these atoms through. So, anyway, side note. Okay, so there's our protons. Okay? Neutrons are neutral. They don't have a charge. They actually have a very similar mass to protons. It's about 1 as well. So we pretty much say they weigh the same. So, when these, actually let's come over here and then we'll do that. Okay, in the cloud are the electrons. Electrons have a negative charge. And the electrons do have mass, because they are matter, but in comparison, it's so small that we kind of just ignore them. So compared to protons and neutrons, electrons have no mass. But once again, it's just a comparison thing. It's kind of like you stepping on the scale, getting a mass, losing a hair, and then getting your mass again. Does it change? Yes. Can we see the change? Not really. So we kind of ignore them when it comes to the mass. But what they do affect is really what this whole class is about, is electrons affect the bonding. Which pretty much is what this whole entire class is all about, is chemical reactions. Bonding, we'll put that, reactions, is all about what these electrons do. So honestly speaking, this side of our flow chart, we really won't talk about a ton. This actually is its own section of chemistry known as nuclear chemistry, which you could go on and take entire classes about nuclear chemistry. You could actually go on and become a nuclear chemist. In terms of our curriculum, it's really not a part of it. So there's a little bit we'll talk about with these guys, but not much. It's really going to be, our focus is going to be these electrons because they control the behavior of it. Now, just as a side note, scientists have discovered that there are smaller things than protons, neutrons, and electrons. It goes into string theory and all sorts of crazy stuff like that. But we're not going to learn that here. But just so you know, there's more to it, and there's probably more after that. That's the crazy thing, is they keep discovering new things as we go. So going back to these and the mass, so if you combine protons and neutrons together, you can determine, so bring those together, you can determine the mass number of an atom. Because once again, electrons are so insignificant that we can kind of exclude them. This number on the bottom of an element on the periodic table, this right here is known as the atomic mass. The atomic mass is the average mass of all an atom's isotopes. And I'll define that word here in a second. I didn't really mean to underline atoms. Isotope is what I want to focus on. Okay, quick brain check. Turn to your table buddy and just remind them, in case they forgot, what part of the atom controls what it is. Protons, neutrons, electrons, go. Okay, good. We all said proton, right? So, you can change neutrons and it still be the same atom. You can change electrons and it's still the same atom. Okay? Atoms that have the same number of protons, so they're the same atom, but a different number of neutrons are known as isotopes of one another. So, for example, carbon can exist with 7 protons. Not 7 protons. Whoop, that's nitrogen. It can exist with 7 neutrons. Carbon can exist with 6 neutrons. It can exist with 8 neutrons. Those would all be classified as isotopes of one another. Now the thing about isotopes is their chemical behavior is identical. Because what determines chemical behavior? Electrons, right? So that doesn't change. They will look the same because they're all carbon, right? The only main difference is their mass, right? A carbon with 8 protons is going to be heavier than a carbon with only 6 protons. Now, when you get into that mass difference, it does cause them at times to become radioactive. That's the main difference with isotopes. We won't, once again, really talk about that because it falls under the category of nuclear chemistry, but that is one of the difference with it. But besides that, there isn't a difference. So isotopes have different mass numbers. For example, we call it carbon-12 when it has 6 protons and 6 neutrons. 6 and 6, there's your mass of 12. Okay, carbon-14 is another isotope, and it has 6 protons and 8 neutrons. By the way, that's just like a little symbol for proton, symbol for neutron. These are isotopes. This number is average from all the known isotopes in the world. Which is why that's what we use. Because when you get a sample of carbon, it's rarely going to be just one particular isotope. It's going to be a blend of them. So, questions on that word isotope? Yeah, Kimberly.
How would they separate different isotopes? Like, how could you just get carbon?
Oh, that was such a great question, but I'm not going to answer it till, what's today, Tuesday? Wednesday? Monday. We'll learn about a device known as a mass spectrometer that can actually separate it by mass because they weigh differently. But yeah, great question. Any other questions on isotopes? Okay, we're going to pause it there because we got 1 minute left. So, homework tonight. Now, this is going to introduce you to what we're learning next time, okay? And then pre-knowledge quiz, and that's it. Don't forget to take your book with you.